Okay, and welcome to the slightly more difficult 2D vector edition. Because in physics we understand that not every motion or vector that we're going to encounter with force, with velocity, with acceleration, is going to go straight up and down or straight side to side. In real life, you encounter things that go at an angle. For instance, what if we had a vector that ended up looking, and let's make it hit the origin, somewhat like this. Right? And we're just going to call this vector A for right now. And let's say that's not the only one. We also have this one over here, put that one on the origin too. And it, of course, is just going to be vector B in that direction. Now, there's two vectors, but I can't add them together by my own rule because they're not all in the Y or all in the X. They have vector components, is what we call it, that make up both of these things. So it has some in the X, some in the Y, and so does B. It has some in the X and some in the Y. And to figure out how these would be added together, we have to end up combining them by finding their component parts. Okay, so what do I mean when I say vector components? Well, we can figure that out by taking a better look here at vector A, okay? Now, if A had a magnitude of, let's just say it was 10 meters per second, right? And it has to be at some sort of angle, right? So we tend to call that angle theta. Let's go ahead and say that that angle is at 30 degrees. Now, we would have to know these two things about it in order to do anything else. But with that, we can figure some things out because it has two different parts. It has a certain amount that it's moving in the X direction and a certain amount that it moves in the Y direction. And so we can actually rewrite that this now has three different parts, three different sides, A in the Y, A in the X, and our original vector A, right, at a 30-degree angle. So we're going to have to calculate what these are, right? And to do that, we need to take a quick trig refresh, because I understand some of you don't remember much of your trig. So when I start talking about trig, I need to think triangles. And I need to think three things. Sine of an angle, I'm going to use theta to represent that. Cosine of an angle. And tangent of an angle. And that they each equal something, right? So you need to remember that sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And if you don't know what I'm talking about with that, think of any right triangle, right? There's our little right triangle thing. And say we have an angle theta is just one of the corners. Well, our opposite will be right there, the opposite side of the angle. Adjacent will be right down here. It is adjacent to that side. And our hypotenuse connects the two. But we can go a little bit further and let's solve our sine and cosine for individual signs of opposite and adjacent. And that'll help us out a lot in our next step with our actual problem. So let's see if we can minimize this stuff and possibly figure out how to solve one of these. Let's start with sine for our adjacent side. And I'll write it in red so that we can see that. So sine of theta is equal to opposite over hypotenuse. Well, this is like any other math problem. All you'd have to really do is multiply both sides by what you want to move over and what will cancel it on one side. So anything that is both multiplied and divided by the same thing is just going to leave that O for opposite side. What you do to one side, you have to do to the other. So we multiply sine of theta by the hypotenuse, and we should get just our opposite side. So we have a brand new equation we can now write, which is h of sine times theta is equal to opposite. And that's how we do it for sine. Now we can do the same thing put that out of the way for cosine. And we can say that cosine of theta is equal to adjacent over hypotenuse. And if we simply multiply both sides by h, that'll cancel out there. And we get the brand new one. Which is h times cosine of theta is equal to adjacent. That will help us out with our original problem. Because in our original problem here, we need to figure out a of y and a of x. But that's just our opposite and our adjacent side, and we know the value for our hypotenuse, we know our value for theta. So we can rewrite this in a simple formula. So a of y is a value times sine of theta, which is going to also be, since we know these values, 10 meters per second times sine of 30 degrees. And after we have that, we can put it in our calculators, and we can get that would actually be 5 meters per second. And we have an actual value for that. In the same way, we can take a of x and say that it's equal to a times cosine of theta, which we're going to rewrite as 10 meters per second times cosine of 30 degrees, which means a of x, when we plug that into our calculator, is equal to 8.7. Yes, it's rounded, it's okay, meters per second. And now we have the value of the two vector components that we need. Now, as you can see, we can also take the second vector, our b vector, and we can break it down in the exact same way in its component parts. So you're going to have a b of y and a b of x. That's going to give us bx is equal to b, that's the hypotenuse, times cosine of theta, our angle, which ends up being 15 meters per second of cosine of 20. B of y is going to be b times sine of theta, because it's opposite. And so we're going to do 15 meters per second times sine of 20 degrees. When we do that, we get values that we can then break down for that. So for b of x, that ends up being 14.1, rounded of course, meters per second. But for y we actually end up getting 5.1 meters per second. But then we have to use our super common sense powers and say, isn't that pointing down? Wouldn't this be in quadrant 4 where our y's are negative? Well, yes. So because of that, we're going to go ahead and make it a negative. So it's negative 5.1 meters per second. And now we have all the vector components we need for b as well as for a. And we can actually start our vector addition.